Uh, Hello everyone. Today we'll discuss Codeforces 1042 round div 3. I'm Suvrat Mehta and we'll discuss problems from A to F for Codeforces 1042 Division 3. So let's start with the discussion. I'm audible, right? Uh, am I audible, guys? Hello. Okay. So I'm audible, I think. So let's start with the discussion. Question A, lever. In divergent universe, the lever iterates itself given two arrays A and B of length n. In each iteration, the lever will do the following. Choose a random index I such that AI is greater than BI, then decrease AI by 1. If there does not exist such I, ignore this step. Then choose a random index I such that AI is less than BI, then increase AI by 1. If there does not exist such I, ignore this step. After each iteration, the lever will check if step 1 is ignored, and if so, it will end its iteration. You are given two arrays, find the number of iterations that the lever does. It can be shown this number is fixed over all possibilities of random indices that the lever can choose for each step. Okay, so basically, the question is uh, I have a lever that iterates itself, and basically it in each iteration it follows two steps. So step one is basically uh, pick a random index I such that AI is greater than BI, such that AI is greater than BI, and then we increase AI by 1. And step 2 for each iteration is pick a number, pick a random index I such that AI is less than BI, and then we, okay, sorry, uh, here we decrease AI by 1, and here we increase AI by 1. And if step 1 is not possible, then we end the iteration. Basically, after each iteration, the lever will check if step 1 is ignored, and if so, it will end its iteration. So basically, if there does not exist such I, then this step is ignored. So if there does not exist an I such that AI is greater than BI, then the iterations end, and we need to count the number of iterations, find the number of iterations that the lever does. So let's see the test cases. The first test case is the first test case is 7356. 7356. So in the first iteration, what will happen? First, we'll follow the step 1, pick a random index I such that AI is greater than BI. This is array A and this is array B. So A is greater than BI for this index, so let's choose that and decrease AI by 1. So it will become 6356. And then for step 2, we pick a random index I and increase AI by 1. So this will become 6456, because this index can be used in step 2 since AI is less than BI. Now this was iteration 1. Now for iteration 2, what will happen? Again, we need to follow the step 1. For step 1, we'll choose the 65 and it will become 5546, and then this will become 5556. because 4 is less than 6, so we increased 4 by 1. This was iteration 2. Now again we try to follow the step 1, but since there is no index where AI is greater than BI, here AI is equal to BI and here AI is less than BI. There is no index where AI is greater than BI. So no index with AI greater than BI. So basically, in this iteration, step 1 can't be followed, so it will be ignored, and then the iterations would end. So the total count of iteration would be 3. That was the answer for first test case. Now the second test case is 314, 314. We can see that all AI are equal to the corresponding BIs. So on the first iteration itself, the step 1 will fail. So the number of total iterations would be 1. Now for this test case, 10, 1. A is 10 and B is 1. So what will happen? We'll choose an index where AI is greater than BI. This will become 9, 1, then 8, 1, then 7, 1, then 6, 1, all the way till 1, 1. So this would be first iteration, second iteration, third iteration. This would be 10th iteration. So answer. And now let's see this test case 114514. 114514 B 191981 191981. So basically now we can follow the 4159. Okay, so we can either choose this index or this index for the first iteration, but since the answer must come out, since it is written in the question, it can be shown this number is fixed over all possibilities of random indices that the lever can choose for each step. So it really doesn't matter which index we choose. So let's just choose the first one. So it becomes 1119 and 3159 1841. So let's now we need to follow the step 2. Let's just pick this index. It becomes 1118 3159 18441. So basically, again we try to do the same. This 3 will become 2, so it becomes let's just apply step 2 on this one and apply step 1 on this one. So 1 yep, just a second. Okay, I'm sorry. Step 2 we apply when AI is less than BI. Here it will be 2 and here it will be 9. Sorry, my bad. Now I'll apply step 2 on this one and apply step 1 on this one. So this becomes 3, 9. This becomes 2, 1, and rest is same. This is iteration 2. And again I apply step 2 on this one and step 1 on this one. So it becomes 1, 1, 4, 9, 1, 1, 5, 9, 1, 8, 4, 1. This was iteration 3. Now we cannot apply step 1 on this one. So let's just apply step 2 on this one and step 1 on this one. So it becomes 1, 1, 5, 9, 1, 1, 5, 9, 1, 8, 3, 1. Then it becomes 1, 1, 6, 9, 1, 1, 5, 9, 1, 8, 2, 1. Then it becomes 1, 1, 6, 9, 1, 7, 9, 5, 9, 1, 8, 1, 1. And now on this iteration, we cannot follow step 1, so end. So how many? 3, then 4, then 5, 6, and then 7. So answer for this test case would be 7. So that was it for the test cases. Now, actually one important observation that I made is since we need in each iteration we follow the step 1 once and the step 2 once. So in each iteration both the steps are followed once, and if step 1 cannot be followed then we end the iteration. So basically we just need to count the number of first steps that we make. That would be equal to the number of iterations. What I'm saying is since in each iteration we do step 1 we do step 1 once and step 2 once, and we end the iteration when we cannot do step 1 anymore. Step 1 anymore. So basically what this means is total number of iterations would be equal to total number of step 1s. Actually total number of step 1s plus 1, because in the last iteration we basically cannot make any further step 1, so that is our last iteration. So in our last iteration we don't do any step 1, and rest all the iterations we do one single step 1. So total number of iterations would be total number of step 1 plus 1. So this is our observation for this question. Now we just need to count the total number of step 1s, and let's just say that a pair is like this. Basically AI is 9 and BI is 4. So what will happen if we just perform the step 1s? This will become 8 4, right? Step 1, yep, 8 4, then 7 3, 7 4, then 6 4, and then 5 4, and then 4 4. So basically the number of step 1s performed would be 9 minus 4 for this particular index. And if some index is like this, basically 6 3, then only step 2s will be performed here. So we don't need to count for these indexes. We only need to count for indexes like this where AI is greater than BI. So for a pair AI greater than BI, AI minus BI uh, times step 1 is followed. So basically what we can do is we can sum AI minus BI for all I such that AI is greater than BI, or we and 1 plus would be the answer. And we can also write this like this: 1 plus maximum of 0 comma AI minus BI. So automatically summation for all I. So automatically this function would be equal to 0 when AI is less than BI, and would be equal to AI minus BI when AI is greater than BI. So basically it would only add these values. So this will give our desired answer. So that was it for the question. We can implement this in O of n, and I'll show you guys the now. What? I think uh, they are not allowing to view the solutions right now. I'll show you guys the solution after some time when I'm allowed to view the solutions. I think, I don't know, maybe my college blocked or something. Are you clear with the solution, guys? You can check in leaderboard. Okay. I'm allowed to hack this. It is not showing the solution. Basically, it would just look like this. Yep. This is it. It would just look like this. Basically, I take input for vector a and b and just add zero, maximum of zero, comma ai minus bi, and that would be just answer. So that was the solution. If anyone has any doubts in this, they can ask. Go to your submissions. It is not a long. Can you guys see the solution? Can you guys open my solution? Just a second. Let me check if I can open on my phone. No part. Okay, I guess let's just move on. Uh, let's just move on. So you guys can see the solution after the contest, after the discussion. The links would be given in the description. Let's just move on for now. So problem B, alternating series. You are given an integer n, call an array A of length n good if for all 1 to I, ai into ai plus 1 is less than 0. That is, the product of adjacent elements is negative. For all subarrays with length at least 2, the sum of all elements in the subarray is positive. Additionally, we say a good array A of length n is better than another good array B of length n if this is lexicographically smaller than this. So, okay, output a good length n array of length n such that it is better than every other good array of length n. And the constraints is n is less than 2e5. So expected time complexity would be around O of n or O of n log n. Okay, so problem B. So we are given a definition of a good array. So a good array is basically if for all I, ai into ai plus 1 is negative. For I 1 to n, less than n, and for all subarrays length greater than 2 equal to 2. Sum is always positive, strictly positive, not greater than equal to 0, because subarray is positive and the definition of positive is given as greater than 0. And also we need to find the best subarray, best good array, find the lexicographically smallest good array. That is our question. So let's see the test cases once. First test case is n equal to 2. So we have two indexes and the multiplication of both of these should be negative. And since we need the lexicographically smallest, so we should put the first element as negative and second element as positive. Since first element, we need to find the lexicographically smallest good array, and we are comparing mod values, modded values. Absolute, I think absolute is better word. Absolute values. Absolute values we are comparing when checking for lexicographically smaller. So basically A and B. So A plus B should be positive due to our second condition, and A into B should be negative due to our first condition. And we need to find the lexicographically array like this. So the answer for that would be -1 and 2, because 1 is the smallest number possible. Also another constraint that we are given is we cannot take any element as 0, because ai into ai plus 1 should be strictly negative. So basically if we take any element as 0, then it won't be strictly negative, it will become equal to 0. So we need to take all the elements as strictly negative or strictly positive. We cannot take 0. So a not equal to 0 and b not equal to 0. So the smallest element that a could have been was 1 or -1. So we had taken -1, and then the second element should be like this, such that a plus b is greater than 0. So b should be greater than 1. So -1, 2 is the best answer for this case. And for n equal to 3, which is the next test case, what we can do is again put the first element as -1, and now we need to put a positive element here and a negative element here. So what we can do is we need this positive element such that let's just put the variables x and y, such that -1 plus x is positive and x plus y is also positive, and -1 plus x plus y is also positive. So since this condition gives us the result x plus y greater than 1, we don't need this condition. So we have two conditions, x greater than 1 and x plus y greater than 1. So y must be greater than 1 minus x, and the smallest value for y that we can take is again -1. So if we take y as -1, then x would be greater than 2. So we need to take x as 3, and we cannot take x any lower than 3, because if we take x as 2, then this equation will become 2 plus y is greater than 1 and y is greater than -1, which is not possible because y has to be negative. So y is greater than -1 will not allow any negative values. So -1, 3, -1 would be the best answer in this case. So one observation that I made is we can just let's say for some good array A, for some good array A, uh, let's say there is some subarray of length 3, A, B, and C. So for this subarray, the total sum should be positive, right? So let's just assume that A is negative and C is negative and B is positive. So for subarray like this, B should be greater than mod A plus mod C. And for a subarray of size 2, AB, let's just say that this is positive and this is negative. So A should be greater than mod B. And we don't need to check for other cases like ABC, positive, negative, positive, because since we already checked for this, so already A minus A would be greater than mod B. So sum of this can never be negative. So we don't need to check for this. So basically B should be greater than the sum of both the adjacent elements. And if these two are followed, then for any subarray we can say that the sum would be always positive, because let's just take a even subarray, even length. So for an even length subarray, let's just say that there are 8 elements. So it can be either minus plus minus plus minus plus minus plus minus plus, and then basically this plus would be greater than this plus. So we can say that this has a positive sum. This plus again would be greater than, so this. If I'm talking about where all the 2 length subarrays and all the 3 length subarrays have a positive sum, so we don't need to check for any length greater than 3. We just need to check for 2 length and 3 length subarrays. So let's say we have checked for 2 length, 3 length. So basically each pair would have a positive value. So the overall subarray would have a positive value. So all the even length subarrays will have a positive subarray sum. And for odd length subarrays, basically let's take 7, 1, 2, 3, 4, 5, 6, 7. So again these two would have a positive sum, and these 3 will also have a positive sum because we have checked for 3 elements also. And if the 3 elements are like this, then also it would be positive because these 2 elements have a positive sum and this is also positive. So basically all odd and all even length subarrays would then have a positive sum. So we just need to take care of these 2 conditions. So B should be greater than the sum of adjacent elements, and if this is true, then automatically this will also become true. So let's just try to construct using this property. So we will get a construction like this, basically -1 3 -1 3 -1 3 and so on. We'll get a construction like this. So for every pair we can see that the sum is positive, and for every triplet also we can see that the total sum is positive. So basically this would be our answer, and there is just one more case. Let's say for n equal to 2, n equal to 4, let's take. So according to us the answer would be -1 3 -1 3, right? But we got this 3 because we had this condition, and since both A and C were given as greater than equal to 1, so B must be greater than equal to 3, because B is greater than sum of A and C, and sum of A and C would be at least 2. So B should be greater than at least 2. So B would be greater than equal to 3. So we got this 3. But in this case, the last element actually doesn't come in any 3 length subarray. It would only come in this. So we don't need to take this as 3, we can just take this as 2, because even now all 3 length subarrays will have a positive score, and all 2 length subarrays will also have a positive score. So for even length we can just put 2 at the end, and for odd length we need to do it like this, because now this element would be a part of 3 length subarray, so we do need to take it as 3. So basically this was for even and odd test cases, so that would be our answer. Let me just write it again. For even it is -1 3 -1 3 -1, and in the end it is -1 2. For odd it is -1 3 -1 3 -1 and this 3. So we can generate this sequence in O of n. I'll again, let me just try to show you guys code. Uh, why not -1 2 -1 2 like this? Okay, so basically let's just take this example for n equal to 3. So if we take this subarray, the sum is 0, but the sum cannot be 0. It was given that sum should be greater than 0. So that's why we cannot take the middle element as 2, we need to take it as 3. Are you guys clear with this question? Um, okay, so how to reach people from newbie? I think you need to practice. Um, my CF ID is Suvrat 6. Okay, wait, I'll show you guys the solution as well. It's opening on my phone now, I think. Okay, just a second. How do I don't know, man. Is it this. Okay. Uh, this is the code for B. Basically, you can just print 3 and -1 alternating, and I'm using a bool pause for false and just setting it as true for just setting it as negative or false for every iteration, so that it it is alternating between -1 and 3, and the pause would be 1 if n is even. So it would end it we can end the sequence with a 2, else we'll end the sequence with a -1. So that was the solution for B. Let's now move on to question C. In a question, why we not take min of both step? In a question, why we not take minimum of both steps? We only need to count the number of step once, because if even if step 2, if the number of step 2s are less than step 1s, even then the number of iterations would still continue, because in each iteration, even if step 1 is, even if we can perform the step 1, that iteration would count, but if we cannot perform step, the iteration won't count. So we need to count the total number of step 1s. So I don't think you guys have any more doubts. Let's move on to question C. So question C is, given two multisets S and T of size n and a positive integer k, you may perform the following operations any number of times on S. Select an element x in S and remove one occurrence of x in S. Then either insert x plus k into S or insert x minus k into S. Determine if it is possible to make S equal to T. Two multisets S and T are equal if every elements appear the same number of times in S and T. The constraints are n is less than 2e5, S is at 10e9, 1e9, and T is also 1e9. So expected time complexity might be O of n or O of n log n. So the question is basically problem C. We have two multisets S and T, and in each operation we can select an element x in S and remove one occurrence of x in S, then insert either x plus k or x minus k mod. So in one operation we can remove x from S and add either x plus k or modulo x minus k in S. And we need to tell if we need to find whether S can be converted into T or not. So let's see the test cases. Let's take this test case 6 2 9 8 4 11. So 6 2 9 8 4 11, and k is given as 5. So what we can, this is S, this is T. We see that we can remove this and add 6 plus 5, which is 11. And then what we can do is we can remove this and add 9 minus 5, which is 4. So now we've got this element and this element. And then we can remove this and add 2 plus 5, 7. and what we okay, wait. We can remove this and add 2 minus 5, which would be minus 3, and then mod would give you 3, and then we can remove this 3 and get 3 plus 5, which is 8. So basically, if we remove x, then we can add x plus k, and we can again remove this and add x plus 2k, and so on we can go. So for any x, we can remove this and simply add x plus ik. So basically, both of these would have the same mod value with x. So for a given x, we can add x plus ik, or what we can do is, for this x, we can keep on subtracting till let's say we subtract k from x I times, and still this is greater than 0. So when we subtract the next time, it would become k minus x minus ik, and x minus ik is nothing but k minus x percentage k. So basically, I'll show you guys this with an example. Let's take x as 20 and k as 5. What we have to do is keep on subtracting k till we can. So 20 would become 15. Wait, let's just take k as 6. 20 would become 14. 14 would become 8. 8 would become 2. And then now when we try to subtract 6 from 2, it would become 4 because we are taking mod. So basically, we subtract till we get x percentage 6, which is 2, and then we get this value k minus x percentage 6. So basically 6 minus 20 percentage 6, which is equal to 4. So for a given value x, we can get two values. We can get x plus ik, or we can get basically k minus x modulo k plus ik. So we can get these two values. Let's just so to solve this question, we just need to check whether all the elements in T are of the form that we can make from S. So basically, some element y in T is of the form a equal to y percentage k and b equal to k minus y percentage k. So if there exists some x in S where, let's say, a dash equal to x percentage k and b dash equal to k minus y percentage x, k minus x percentage k, and so if a is equal to a and b is equal to b dash, or a is equal to a dash and b is equal to b dash, a is equal to b dash and b is equal to a dash, then we can convert x in y, x to y. This is our observation. I'll just prove my statement again in just a second. So basically what I'm saying is, if there is some element y in T such that a is y percentage k and b is k minus y percentage k, and also in S there is some element x such that a dash is x percentage k and b dash is x minus k percentage k, k minus x percentage k. So if either of these two conditions follow, then we can say that x can be converted to y. How? So basically we know that we can convert, we can add x, we can add k to x as many times as we want, so we can make x as x plus ik, right? Also we can subtract k, so we can transform x to k minus x modulo k. So we can either keep x as x, or we can make x as k minus x modulo k. So if any of these two values, so basically let's say that we have x equal to 2 and y equal to 3, and let's say k equal to 5. So for this, a would be 2 percentage 5 as 2, and b would be, sorry, a dash and b dash, a dash would be this and b dash would be this, 5 minus 2, which is 3. And this a would be 3 percentage 5, which is 3, and b dash, b would be 5 minus 3, 2. So we see that a dash is equal to b and b dash is equal to a. So we can say that x can be converted to y. How? Let's just since we have this is equal to this and this as equal to this, right? So we can just go from x to k minus x modulo k, which is nothing but, since this value is equal to this value, so we just made our x as a, and since a is nothing but y modulo k, so a plus ik would be y. So we went from b dash, we went from x to b dash, and then b dash is a, and then from a we can get y. Either we can follow this route, or if this is true, then we can simply go from x to a dash, which is a, and which will get us y. So any of these two conditions, if they are true, then we can go from x to y. So now we need to check whether each of the y can be formed using the elements in S, right? So what we can do is we can create a map, and for I in A, we can just add I percentage k in the map and k minus I percentage k in the map. So what this will do is, this will add all the a dash and b dash inside the map, count of a dash and b dash, and then for I in sorry, not a, basically S and T, what I can do is I can now start subtracting the pairs. So first I will increment the values for a and b, and then I will decrement the values for a dash and b dash. Am I not audible, guys? Hello. Wait, was I not audible? Okay, I'll just go through the solution again. Um, So basically, for an element x in S, I can remove this element and make it x plus k, or I can make it x minus k modulo, absolute of x minus k, right? So if I follow this step, then I can make x in x as x plus ik, and if I follow this step, then I can make x as k minus x modulo k. I can go from x to x modulo k, and then from x modulo k I'll get k minus x modulo k. So for an x, I can either convert it into x modulo k, or I can convert it into k minus x modulo k, and then I can just add k to the value. So this will, for an x, I can get any of these elements, x modulo k plus ik, or k minus x modulo k plus ik. From an x, I can get any of these values. I is equal to 0 to infinity, right? I is 0 to infinity. So for an x, I can get any of these values, any of these. So now I need to check whether for an x I can, for each x I can get an element in y. So what we can say is, we can just add the values of x modulo k in map and k minus x modulo k as well for I in S. And then for I in T, what we can do is we can subtract these values, I modulo for y in T and x in S. So we can subtract these values, y modulo k minus minus and m of k minus y modulo k minus minus. So what this means is, for every value I am adding 1 in the map, and for every value y I am subtracting 1 from the map. So basically subtracting means that I am forming the pair between those two values, since if some y has basically y modulo k, let's say as a, and k minus y modulo k as b. So now if x modulo k is equal to a, then we can convert x to y, because simply we just need to keep adding k in x till we reach y, or keep subtracting k from x till we reach y, because both have the same modulo. Else if k minus x percentage k is equal to a, then basically we can again go from x to y, since for an x we can just transform x into this value first, and now since this value is equal to a, we can just add k till we reach y. So again we can go from x to y. So if any of these two conditions hold, we can go from x to y. So if either m of y percentage k or m of k minus y percentage k was in the map, then we can just remove the pair from the map. And if in the end all values in map are 0, then we just see out yes, else no. Did you guys understand the solution? I was audible this time, right? if x percentage k is equal to y percentage k, or k minus x percentage k is equal to y percentage k, then possible. Okay, that is correct. If x percentage k equal to y percentage k, or k minus x percentage k is equal to y percentage k, then possible. Okay, I think you copied and pasted it twice. Can we store minimum of x percentage k and k minus x percentage k and compare with minimum of y percentage k and k minus y percentage k? Mm, I think you can create two arrays with the values of just a second, let me be sure about that. X percentage k and k minus x percentage k. Okay, so if we take minimum, um, yes, I think, yep. So basically, if we create two arrays where for each value in x, we just take the minimum of x percentage k and k minus x percentage k, and for each value y, we create the element minimum of y percentage k and k minus y percentage k, and we basically sort the arrays and compare if both the arrays are same or not. Then we'll basically, if they are same, then x can be converted into y, s can be converted into t, basically because for each element we are storing the lowest value that we can get for that element. So yes, your wait, yes, your solution is correct, Ayush. Did you understand? Okay, so let's go on to question D. Oh, I'll show you guys code for C. Just a second, let me send it to myself. Missions. I can still not open it, right? Why am I not allowed to open it on laptop? So, yep. This is the solution for C. Basically, I put the values x percentage k and k minus x percentage k in the map, and then for the next multiset, I remove those values. And in the end, if there is any element in the map with a positive frequency, then I see out no, else I see out yes. So time complexity would be n and log n, since insertion in map is log n. So n log n is the time complexity. So that was it. Let's move on to the next question. Okay. So Kagari is preparing to archive a tree and she knows the cost of doing so will depend on its diameter. So to keep the expense down, her goal is to shrink the diameter as much as possible first. Then she can perform the following operation on the tree. Okay. Uh, choose two vertices S and T. Let the sequence of vertices on the simple path from S and T be V0, V1 to Vk, where V0 is S and Vk is T. Remove all edges along the path. In other words, remove edges V0, V1, V1, V2, and okay. Connect vertices V1, V2, Vk directly to V0. In other words, add edges. Okay. It can be shown that the graph is still a tree after operation. Help her determine the minimum number of operations required to achieve the minimal diameter. So n is, since n is 2e5, so again the expected time complexity would be O of n log n. So problem D. So basically we are given a tree and we can perform operations. What is an operation? We can choose two nodes u comma v, and let's say u0, u1, u2 till uk were on the path from u to v. So this would be u and this would be v. So we will delete all these edges. These edges would be deleted, and we will connect these directly to u. I'll show you this operation through an example. Uh, let's take this example 1 2 1 3 2 4 1 2 1 3 2 4. Let's add another node, I think 5. Okay, so let's choose the path from 3 to 2. So it is these three nodes, and let's take 3 as u and 2 as v. So we need to delete these edges, and after deleting, the graph would look like this: 5 1 3 2 4. And now we need to connect these. We need to connect all the nodes in the path to the starting node, and we need to minimize the number of operations to get the tree with the minimum diameter. Right. So first of all, what is a diameter? Diameter is the length of longest path in a tree. Longest path in a tree. Also, now basically what could be the minimum diameter of any tree? For that, I think if n is greater than 2, then the tree must look like this. So now it has a path which has length 3. For any tree which has n greater than equal to 2, for any tree with n greater than 2, it will have a path of length 3. Right. So since diameter is the longest, is the length of the longest path in the tree, so diameter would be greater than equal to 3, right? And since we need to minimize the diameter, if we somehow transform any tree, basically if we somehow transform any tree like this, there will be some node u in the center, and all the other nodes would be attached to this u node itself. So then now we will not have any path, basically this. Now we will not have any path which has length greater than 3. So in tree like this, the diameter would be 3. If any child of u has another child like this, or so, then the diameter would increase from 3, it would become 4. So we need exactly this setup of tree to achieve the minimum diameter. Let's try to solve another test case and let's see what we find. I'm audible, right? Yep, I think I'm audible. So let's try for this tree. 1 2 1 3. 1 2 1 3. Then 2 4 3 5. 2 4 3 5. 3 8. 5 6 5 7. 7 9 7 10. 7 9 7 10. And 5 11. So 5 11. This is the tree. So we need to make this tree like this, right? So what we can do, let's say, let's just try to fix the node in the center and then try to find the minimum number of operations to transform the tree like into this tree. And for all the centers, let's find the minimum let's find which center takes the minimum number of operations. So let's try this. Let's say the center is 1, so every other node must be connected to 1. So what we can do is first we'll take this path, and then 2 and 4 would be connected to 1. So we need one operation, and then again we can take this path. So basically we can count the number of leaf nodes kind of, because we need to connect all these nodes to 1, right, to transform the tree into this. So we need to connect all the leaf nodes to 1. So we need to take the path from leaf node to 1, and if we take that path, then one would all the nodes in that path would be connected to 1. And since after each operation the structure is still a tree, then we will always have another path from other leaf nodes. So basically for this one, what we need to do 1 2 3 4 5 6 operations so that all the nodes are directly connected to 1. Let's see for this too. Let me just erase this. Okay. So for this too, sorry, for this too, now we only need to perform this and this operation, because 4 is already directly connected to 2. So basically we don't need to take this path. Since 4 is already a direct connection to 2, we just need to directly connect these nodes. So 1 2 3 4 5. 2 will take 5 operations, and then 4 will again take only 5 operations. Then for 3 we need again 5 operations, because 8 is directly connected to 3. Then for 5, 6 and 11 both are directly connected to 5. So 1 2 3 and 4 operations. And for this again we need 5, and this again we need 5, and for this we need 5 again. For this also we need 5. For this now again 2 leaf nodes are connected, 9 and 10, so we need only 4, and this also we need 5. So the minimum number of operations that we need to do is 4. So this would be our answer for this test case. So basically the solution is like this. We need to count number of leaf nodes not directly attached to the center node, because if we attach all the leaf nodes directly to the center node, then all the other nodes that are in between would be automatically attached to the center node, because they would be in the path to the leaf node. So we only need to attach the leaf nodes. So this is our observation, and the minimum of this, taking each node as center node, would be the answer. So now we need to just count this for each node, right? So how do we count this for each node? We can maintain total leaf count, and from this total leaf count we can just subtract the uh, number of adjacent leaves, basically the nodes which are adjacent to the center node and are a leaf. Basically for this 7, 9 and 10, and also minus 1 if the center node is a leaf node itself. So basically, like in this case, 8 was itself a leaf node, so now there were only 5 other leaf nodes that it had to connect to itself. So answer for 8 was 5. So basically minus 1 if the center node is leaf node itself. So basically this we have already calculated, so this is O of 1 and this would be O of child, and this is O of 1. So for each node we are taking O of child complexity, so sigma O of child for each node. So this is just the number of edges. So the overall time complexity would be O of n plus m, which is well within the limit. So I'll show you guys the code now. I still can't open it, right? No. Wait a second. Okay. So basically, I take the input as an adjacency list, and then this I don't think this is required. Okay, and then I maintain the variable total leaf, and I just to add total leaf if adjacency of I has a size of 1. Basically, any node that has only one other node that is connected to, then it's a leaf node. So total leaves plus equal to adjacency of I dot size equal to 1, and then CT is the number of operations that I need to do if I is the center node. So CT would be total leaf minus 1 if the current node is a leaf node, basically this one, and then for all the childrens of I, if adjacency of J has a size equal to 1, then CT minus 1, basically this, and then I just take the minimum of all CTs and that would be my answer. So did you guys understand the solution? Did you already know approach for this question, or you tried some big examples? I understood the approach after seeing the test cases. total leaf minus max left underscore node in a node. What is max left underscore node? So if you guys have any doubts, you can ask in the chat. Okay, so I think we can move on to the next question. So problem E, adjacent XOR. So you're given an array A of length n for each index I such that 1 is less than I is less than n. You can perform the following operation at most once. At most once, right? So assign AI as AI or AI plus 1, where XOR denotes the bitwise XOR operation. You can choose indices and perform the operations in any sequential order given another array B of length and determine if it is possible to transform A to B. Okay, so n is given less than 2e5. So expected time complexity would be, I think, O of n or O of n log n. So basically problem E, we are given an array A and we can perform the following operation. AI is, we can set AI as AI XOR AI plus 1. And we can perform this at most once for an I. This is very important. This will come in handy later. And we can perform the operations in any order of I. And we need to tell if A can be converted into B. So let's just see one test case first. 1 2 3 4 5 3 2 7 1 5. A is 1 2 3 4 5. B is 3 2 7 1 5. 3 2 7 1 5. So what we can do is I see that 1 or 2 is 3, so I can just remove this 1 and put it as 3, and 2 and 2 are already same. 3 or 4 is again 7, so I can just do this, and then 4 or 5 is 1, so I can do this. So the answer for this test case would be yes. Let's see, I think this test case, let's see, 1 1 4 5 1 1 1 4 5 1 4 0 5 4 5 5 4 0 5 4 5 5 4. Okay, so 1 or 1 is 0, so I can just do this. Then 1 or 4 is again 5, so I can do this. Then 4 is already same, 5 is already same, 1 or 4 is again 5, so I can do this. So the answer for this test case again would be yes. So these two test cases were yes. Let's take this test case 0012 13332. 0012 and 1332. So we cannot get 1, we cannot get 3. 1 and 2 give us 3, so we can perform this operation and we'll get 3. 3 is already same, 2 is already same. Now we can do zeros or 3 and we get 3 here, but still we can't get 1. So let me change this test case a little bit and let's solve for this 3012 and 1332. So basically we can perform the operation on this index I, because 1 or 2 is 3, so I can just change this from this to this. Now 3 is done and 2 is done. So now we can see that 3 or 0 would be 3, so we can put this as 3. And sorry, let me just put 2 here. 2. So now 3 or 2 would be 1. So in this, if this was the test case, then the answer would be yes. For this, the answer was no. So basically, let's see this condition. What does this mean? Since we can only perform once, first of all, the index I can only be used to change value of I minus 1, right? So, and I, because only I minus 1 and I involve the operation with I. Since I minus 1 gets changed to I minus 1's or I, and I gets changed to I's or I plus 1. So I is only important for I minus 1 and ith indexes. Now let's check. Now let's talk about this condition. So basically, we can perform one operation only once. So what does this means? An index, the value of an index, can be changed at most once. Right. So let's say there is some I, there is some AI, and there is BI, there is AI plus 1 and BI plus 1. So also one index will have at max of 2 different values at any point during our operations. Like it may, the operation on ith index, we still might not have performed that operation, so that will mean that AI would have its initial value, or if we have already performed the operation on the ith index, then that must mean the AI will have its final value. So the value of any index should be either the initial value or the final value after the operation. So basically, one index will have at max of 2 different values. So if AI XOR initial of AI plus 1 is not equal to BI, and AI XOR final of no AI plus 1 is not equal to BI, then we can say that AI cannot be transformed into BI. Hence, the answer is no. Right. If any of these two is true, then we can perform the operation and the answer might be yes. Right. So, how can we check whether all the indexes, how can we check for all the initial and final values for all the indexes? We need to check for all, right? So what we can do is we can follow this simple procedure. We can first go from left to right. Left to right. So what this will do is, basically, let's say we have an array and we are going from left to right. Also, since we can only perform the operations at max 1 for an index, then we need to make sure that after the operation the index would have its final value. Basically, BI should be equal to AI XOR I plus 1 if we are performing the operation. Right, AI should get equal to BI after the operation. So what we can do is we can go from left to right, and we can see that there would be A1, A2, A3, A4, A5 till AN, and there will be B1, B2, B3, B4, B5 till BN. So what we can do is we can check if A1s, or basically when we are at this index, all the indexes in front of it have initial values, right? Initial values. So we will check whether A1 can use the initial value of A2 to become B1. If it can, we can just erase this and make it as B1. Or if it cannot, then we'll just leave it as it is and move in front. And then we'll check if A2 can become B2 using the initial value of A3, and we can just iterate through the array. And then we will have checked for each of the elements that can we use the initial value of the next element to get BI. Now after this iteration, some of the elements, the values would now be the final values. So what we can do is we can go from right to left. We can go from right to left and do the same. Basically, again A1, A2, A3, A4, A5 till AN. We can put our pointer here, and now when our pointer is here, we can check if we perform the operation on this element, can we get the value BI? If we get the value BI, so basically when we are at some index, all the values in front of it would be having final values. Since for any AX here, we have already checked AX with the initial value of AX plus 1 and in the final value of AX plus 1. So AX would now have the final value of it, because we have already tried to XOR it with the initial value and the final value of AX plus 1. So when we go from right to left, we will be setting each element to its final value, and the previous element would now get the chance to take XOR with the final value, and if it can attain the value B, value corresponding in B, then it is good, and if it cannot, then the answer would be no. So we can just follow this procedure. We can go once from left to right so that every element is compared every element tries to XOR with the initial value of the next element, and then we can go from right to left, so that every element tries to XOR with the final value of next element. And that way we have checked for the XOR with initial and final both the values. So if any element is still not able to get the corresponding value in B, then the answer would be no, else the answer would be yes. So we can just implement this in O of n, and I'll show you guys the code. 1 second. Uh, okay, so oh no, this is the last question. I need to get for E. Just a second. E. Okay. So basically, I take the input A and B, and this is the initial from left to right loop. Here I try to XOR AI with AI plus 1, and if it is equal to BI, then I just set AI as BI, and then I go from right to left, and then I again try to XOR. If it is equal, then I just set, and if AI is not equal to BI after performing both the for loops, then the answer is no, else the answer is yes. So okay. Can you explain the right to left part again? Let's take that example 0 1 0 0 1 2 1 3 3 2. 0 0 1 2 1 3 3 2. So what will happen is basically, let's go first from left to right. So for this 0 we cannot do anything, for this 0 we cannot do anything, for this 0 we cannot do anything, but for this one we can take the XOR of 1 and 2 and make it as 3. Now we'll do our second iteration from right to left. So the last element we cannot change its value, so it will always be in its final value. So we check for 3, we try to solve it with 2, we get 1, so we just skip this. Then we check for 0. Now these two are at the final values. Now for this 0 we try to take XOR with 3 and we get 3. So now this also gets its final value. Oh sorry, in the example we have 2 here. Okay. Now this has final value, and now we try to take XOR of 2 and 3 and we get 1. So this also have its final value. That's how this right to left part works. Did you understand? Nahin bin Kaisar. Okay, so if anyone has further doubt, they can ask. Okay, so I think we can move on to the next question. So Unjust binary life. Yuri is given two binary strings A and B, both of which are of length n. The two strings dynamically define an n into n grid. Let I comma j denote the cell in the ith row and jth column. The initial value of cell ij has the value ai or bj, where XOR denotes the bitwise XOR operation. Yuri's journey always starts at the cell 1, comma 1. From a cell I, comma j, she can only move down to I plus 1 or right to ij plus 1. Her journey is possible if there exists a valid path such that all cells on the path, including 1, comma 1, have a value of 0. Okay. Before her departure, she can do the following operation for any number of times. Choose one index I between 1 to n and flip the value of either ai or bi. 0 becomes 1 and 1 becomes 0. The grid will also change accordingly. So let fx comma y denote the minimum required operations so that Yuri can make her journey to the cell xy. You must determine the sum of fx comma y over all 1 to n x comma y. Note that each of these n square cases is independent, meaning you need to assume the grid in its original state in each case. That is, no actual operations are performed. So the length of string is given 2e5, so expected time complexity would be n or n log n. So basically, problem F, we are given two strings A and B, two binary strings, A and B, and a matrix. Let's just say a matrix will have its ith and jth. So I, jth element as aij would be equal to ai's or aj. Now the question is, we need to go from 1, comma 1 to ai, comma j, and we can only take the path where each cell has a value of 0. So if the values are like this, we can take this path. So if we can take this path, then this path is valid. So basically, in one operation, we can flip one bit. We can either flip ai or we can either flip bi in one operation. And we need to find the minimum number of operations. Not actually minimum. Let's just define f of I, comma j as minimum number of operations to go from 1, comma 1 to I, comma j. So f of I, comma j would be minimum number of operations to go from 1, comma 1 to I, comma j. Operation is basically bit flipping, either flipping ai or flipping bi. And in this question, we need to find summation I equal to 1 to n, j equal to 1 to n, f of I, comma j. So for now, let's just try and focus on finding the value of f of I, comma j. Let's not try to optimize the solution to O of n or O of n log n. Let's just try to think what can be the value of f of I, comma j. So let's just say that let's just say that we need to go from here to here, and we are following the path this. We are following this path. So since this is 0, then ai and bi must be same, right? And since again this is 0, then bi plus 1 should also be same as bi. And since again this is also 0, then ai plus 1 would be also equal to bi plus 1, which was equal to bi, which was equal to ai. So ai is equal to ai plus 1 and bi is equal to bi plus 1 for now. Now again, since this is 0, then ai plus 1 would be equal to bi plus 2, and ai plus 1 was equal to a1, so bi plus 2 is also equal to b1. Again similarly, since this is 0, ai plus 2 would be equal to bi plus 2, and since bi plus 2 is equal to b1, so ai plus 2 will also be equal to a1. So basically, for a path, we notice that for a path to exist from 1 comma 1 to I comma j, string a, let's is 1 equal to a2 equal to till ai equal to b1 equal to b2 equal to bj. So the strings till I and j must be all equal elements, because let me show you this once more. I think this might be confusing. Let me draw a matrix. So let's just mark the indices 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. And let's just say we are going from here to here, and we can take any path. We can take maybe this path, right? So a1 is equal to b1. Since this is 0, then a1 XOR b1 XOR should be 0. a1 XOR b1 should be 0. And if the XOR of two numbers are 0, then a1 must be equal to b1. So we get that a1 must be equal to b1, right? And now again a1 must be equal to b2. So again a1 must be equal to b2. Then b2 must be equal to a2. b2 must be equal to a2. Then a2 must be equal to b3. a2 must be equal to b3. b3 must be equal to a3, and a4 also must be equal to b3. A4. Then again a4 must be equal to b4, and then a4 must be equal to b5. So basically we can say that all these elements must be same. Must be same. So we have found out a very important property. For a path to exist from 1 comma 1 to I comma j, a1 equal to a2 till ai equal to b1 equal to b2 till bj, right? This is very important. So let's now use this property to find out f of I comma j, right? That was our target initially. So for a path to exist, now we can take two cases. This can either be equal to 1, or this can either be equal to 0, or this can be equal to 0. So any of these two cases must result in the most optimal answer, right? So we need to follow this. Let's calculate the number of bit flips required in this case, where all are equal to 0, right? So we need to flip all the ones that are in these values, right? So what we can do, we can easily use prefix sum. Let's just skip over a step and directly use prefix sums. So prefix sum in A would give us the number of ones till the ith index. So prefix sum in A till I plus prefix sum in B would gives the number of ones jth till again ith index. So prefix sum ai plus prefix sum bj would be f of I comma j. Not exactly f of I comma j, because this is only for the case when 0 is optimal answer. When 1 is optimal answer, this would be just I plus j minus pf a of I plus pf b of I, b of j. Basically, we were flipping all the ones here, and we were flipping all the zeros here. So we can say that f of x comma y would be the minimum of just a second, pf of ai plus pf of bi comma I plus j minus pf of ai plus pf of bi bj, actually j here also. So we can define f of xy like this. So now we have got a method to calculate f of xy in of 1, but still calculating for all pairs I comma j would take us would be a n square solution that wouldn't pass in this case. So we need to further optimize this. So now I'll use a very good trick that is commonly used in CP. Basically, minimum of a comma b is nothing but a plus b minus modulo a minus b upon 2. How? Let's just open this function. Let's just take that a is greater than b and open this function. So this will become a plus b minus a minus b upon 2. So this is 2b upon 2b, which is b. So b is less than, b was the less than here, so that is correct. And now let's take a is less than b, so this will be a plus b minus b minus a upon 2. So this is 2a upon 2, this would be a. So we can now remove this minimum function from this f of xy. That will help us in calculating the total summation. So now the new f of xy would be, let me, yes, okay. So the new f of xy would be let's just let me, a would be pfa of I plus pfb of j. So pfa of I plus pfb of j, and d would be I plus j minus a. So I plus j minus pfai plus pfbi, right? So let's put the value in this equation, this one, a plus b minus mod a minus b. So a plus b would be I plus j minus mod a minus b. So modulo a minus b would be 2 times prefix pfa of I plus 2 times pfb of I and minus I minus j. So modulo also absolute or mod, whatever. So this is upon 2. Let's just forget about upon 2, we can later just divide by 2. So f of x comma y, let's just denote this as 2 times f of x comma y. That would be simple. Okay, so 2 times f of x comma y would be this. Now we have removed the minimum from our summation. Now we have gotten this next new term that we need to, still we cannot directly calculate this in some better complexity. Still we need to take the O of n, still we have the O of n square solution with us. Let's try to further see what happens. So let's try to see when this, let's try to separate the I and j's in this absolute. So let's make it 2 times, let's make it 2 pfb of j, here j minus j, let's take a minus common, and I minus 2 pf a of I modulo. Okay. So what we can do is we needed to find this, right? I equal to 1 to n, j equal to 1 to n, f of x comma y. Let's try to find this value, f of I comma y, j equal to 1 to n. If we find this value in O of 1 or O of log n, then we'll be able to find this whole summation O of n, O of n log n or O of n. So now let's make our problem that we need to find this in O of log n or O of 1. So we have gotten this function 2 of f of x comma y, and we have this modulo inside. Now since we have already put I as constant, so now this term would become a constant for us, and this term would also become a constant. So let's try to put the summation. So let's try to sum for j equal to 1 to n I plus j minus modulo 2 pf bj minus j minus I minus 2 pf a I, right? Mod and then bracket. So summation I would just become I into n, summation j would just become 1 plus 2 plus 3 till n, which is nothing but n into n plus 1 upon 2. So n into n plus 1 upon 2, right? And now I have this summation j equal to 1 to n 2 pf b of j minus j, and let's just denote this as some constant ci, right? Because it is currently a constant for this summation. So let's just denote it as ci. Now our problem is to solve this summation. How do we solve this? What we can do is 2 pf b of j minus j, this minus ci, and we are taking the absolute of this. So what we can do, since we have to sum for j equal to 1 to n, right, we can just find out for what values of j this term is bigger than this term. So when this term is bigger than this term, the summation would open like this: 2 pf b of j minus ci, and when it is smaller than it, then the summation would open like this: 2 pf b of j plus j, right? For some values of j where 2 pf b of j minus j is less than ci, and where 2 pf b of j minus j is with greater than equal to ci and is less than ci, right? So I can break this summation into these two summations. Now these two summations we can solve easily. How we can create? We basically need the sum of values of 2 pfb of j minus j when till they are basically what we can do is create another vector v, let's say, and vi is equal to 2 pf b of I minus I, and let's sort this vector. So after sorting, what we can do is we can apply binary search to find the largest element that is smaller than c. So when we find the we can find the largest element that is smaller than c in log n complexity, which is nothing but lower bound. And for when we use lower bound, let's just say we get the index x. So what we can do is, now this formula is translated into this, basically v of I minus ci, and I is just x plus 1 till n plus v of I minus actually let's take the upper bound, that would be better. So let x be upper bound. Yep, x would be upper bound. So we can take I equal to x to n and I equal to 1 to n ci minus v. So now to solve this in O of 1, we can simply just use a prefix sum for the vector v, and this would just become prefix sum of vector v minus prefix sum vector v of x minus 1 plus prefix sum vector v of n, actually n not x minus 1. So you get the idea, right? So we can now basically easily solve this in O of 1 and easily solve this in O of 1, and so we can now find this in O of log n, basically including the binary search. So O of log n, and these are just constants. So we are finding this term in O of log n. So we'll be able to calculate this whole term in O of n log. That was the solution for this problem. I'll show you guys the code now. Just a second. Okay. So this is pre-A and pre-B are just prefix sums, basically containing the number of values, number of ones till the ith index, and prefix B is containing the number of ones till the ith index in B. Then a B need is basically this thing, this V, whatever I've written that, this 2 times prefix bi minus I. So 2 times prefix b minus I. So what I can do is I am sorting this v. I was sorting this v, and then I am just taking a prefix sum for this b need, and this prefix sum in b need. What I can do is I am creating another vector cmp, which is basically the first elements of b need, so that I can perform binary search. So index is giving me the upper bound of I minus 2 into pre-ai. So basically ci was I minus 2 prefix a of I. So I'm finding the upper bound of this, and then I'm just adding these two summations in my answer. These two summations, these two. So I'm just adding these two summations, and that would give me the total answer. So is the solution clear to you guys? The E code that you gave is not working properly, I guess. I think I gave this code, right? E. It is working. What can be the rating of C question? What was C again? I forgot. I think 1000 or 1100. And how to do I improve my thing for the next DF questions? Just keep participating in contests and keep up solving them, and you will get better eventually. So you guys can ask any doubts if you have any doubts in F. How to improve bit manipulation? Um, if you need to improve some specific topics, you can just filter out the problems. You can probably, they have, I think, bit masks as a tag, problem tag. So you can put the problem tag bit mask, or you can put the problem tag math, and whatever rating you are stuck at currently, whatever rating you feel difficult for bit manipulation questions, you can practice at that rating, and slowly you will try to, you slowly will try, slowly will start solving those problems easily. So I think bit masks, yep, they have that bit mask tag. You can just solve from here. So I think you guys don't have any more further doubts. So I'll end the today's discussion. Thank you.